Now today we look at the teaching video on differentiation of trigonometric functions. When we talk about trigonometric functions, we're talking about the basic ones like sine, cos, tangent x. There are three functions here we look at. Now this symbol you have seen, that is d over dx. What we mean is this, to differentiate the function sine x. And you notice that sine x is in terms of x. So it's going to be mechanical. There are a few things you need to remember. First, when you differentiate sine, what it gives you. The result is, if you differentiate sine, you get cos. And this thing in the bracket is the angle. If it appears in algebraic form, we call it the algebraic angular expression. So the result of differentiating sine x will give you cos x. To help you remember this better, you just think sine will give you cos. You say a couple more times, you remember this. Next, we have differentiation of cos x. That will give you negative sine bracket x. Now, sometimes when we learn, we seem to ask a lot of questions. If sine give me cos, then cos should give me sine. But remember, this is the rule that we're dealing with. So it's not a lot of explanation we can do about this without going further. So for this level, what we need to do is just to remember, when you differentiate cos x, you get negative sine x. The last one we look at is tangent. If you differentiate tangent x, you should get secant squared bracket x. Again, I would say you will ask a lot of questions. Why here no square? Here you have a square. Just remember this. Sine will give you cos in differentiation. Cos will give you negative sine. And then tangent will give you secant squared. If you remember this, you will do well. I want us to take it a step further. So I want to extend the trigonometrical functions to include expressions beyond just x. You notice that we had the angular expression x. Now I want to have something like ax plus b. This is linear. Just as that one. But this is the full form of the linear expression. We'll run through the same few functions, the sine ax plus b, cos ax plus b, and then tangent ax plus b. The first one here, y equals sine bracket ax plus b. If we differentiate this expression, because the subject is y, then it will be dy over, you look at this expression here. Sine is a function of x. So you will have dx here. Now just remember the rule we had. If you differentiate sine, you're going to get cos. and this is the angular part. It will remain the same. But beyond that, there is something to consider. This expression has to be differentiated once more. So over here, I will have the differentiation of ax plus b. Take it one step more. When we differentiate the x terms, just a reminder, ax is actually ax to the power 1. The index multiply to the coefficient of ax. So 1 times a is a. So we actually get a. This is a constant. When you differentiate a constant, you get a 0. So to rewrite this, you have a cos bracket ax plus b. So that will be the result of differentiating sine bracket ax plus b. Now this is a short way of doing things. Let me just introduce to you the chain rule. Perhaps then you have a very firm form to rely on. This is another presentation for you. Now, if I let this be u, and u can be rewritten in terms of x. So you have ax plus b. Now, if u is to replace ax plus b, then y will be sine u. You have two equations now. So to differentiate the u expression, because the subject here is u, so you have du, and u is in terms of x, dx. This is an x term. The simple way to remember is drop the x, keep the a. If you like to think it the proper way, index 1 multiplied to a is a. The index reduced by 1, you have x to the power 0, which amounts to 1. Differentiate the constant, you get 0. Here, the subject of this equation is y. So dy over, now u is a function, sine is a function of u. So du here. Differentiate sine. The result we remember is cos u. So let me introduce to you now the chain rule equation. You can see this name here help us remember one thing. Chain has links. So one thing linked to another. You can see you have two functions. The function u is in terms of x. And the y is in terms of sine u. So you can say it is a function in a function. So linked up that way. So that will help you remember when we talk about the chain rule, it is a function in a function. So the simple equation is this. Now these are symbols. Symbols cannot be detached or cancelled off. But for the sake of helping you see the logic of it, if I just cancel off du and du, you do get back dy over dx. I want to caution again, they are symbols. They cannot be cancelled off. But to help you remember, cancel off dy over dx, which is the same as what you have on the left-hand side. Now we take those values we had before, or the expression, dy over du is cos u. Put it in there. And the du over dx is just a. So if I simplify this, a, bring it to the front as the coefficient, cos, and u is actually ax plus b. So we have ax plus b. Now, if you recall what I just did before this presentation here, I changed sine to cos. The angular expression remained the same. Then I went one more step, differentiate this angular expression. I got an a, which now I put in front. So the two approaches are the same. But these, I would say, lay out for you systematically. Of course, if you're sitting for O-level, I would not encourage you to write in full like that. You would actually go into the shortcut approach. Meaning, sine, differentiate, you get cos. Then differentiate the angular expression to give you the coefficient here. If I look at y equals cos bracket 2 ax plus b, the symbol of differentiation, dy over dx. Remember that when we differentiate cos function, we get negative sine. So negative sine bracket ax plus b. That remains the same, but you differentiate the angular expression once more. You get a. So, just a reminder, this is d over dx of the angular expression. And this is just your result. Cos will become negative sine. So create the mental picture every time you do a practice so that this will become second nature to you. I think now we try to refresh your mind on what we did for the chain rule. So this time round, we start with the chain rule. We let u be ax plus b, which is the expression over here. In so doing, I can write my y as tangent u. This equation, if I differentiate, I will have du over dA, u the subject, x because the expression is in terms of x. Differentiate the x terms, you get the coefficient. Differentiate the constant, you get a 0. Here, dy over dx. Oh, do you know why is not dy over dx? First, this expression the function is a function of u. So here should be a du. So differentiating tangent u, I get secant squared u. And the chain rule is dy over dx, dy over du times du over dx. Now this is a matter of dropping in the expression dy over du into here. So we get secant squared u. And you have du over dx, we drop it in here, a. So the overall result, a. Now this secant squared u, the u will replace it with ax plus b. So if I think shortcut for this question, then I will take differentiation of tangent, giving me secant squared. The angular part remains the same. Then I'll differentiate the algebraic expression here for the angular expression. Then it will become a, which I'll put as a coefficient of secant squared. The observations you make: sine to cos, cos to negative sine, tangent to secant squared. And you also remember this. This is the angular expression. It will remain the same. So the summary is this. Differentiation of sine will give you cos. The angular part remains the same. And then we have to differentiate the angular expression. And the result will form the coefficient of cos function. That is a plus. Now, if you look at the differentiation of cos, cos will give you negative sine. Then the angular expression remains the same. And we have to form the coefficient by differentiating the angular expression. So basically, two parts to remember. The function after differentiation becomes what? Like its tangent will become secant squared. Of course, the angular expression remains the same. Then the second part is that to form the coefficient, you differentiate the angular expression. That is the summary for the section of work. We go through the last type, in which you will have sine to the power n bracket ax plus b. You also have cos to the power of n bracket ax plus b, and tangent to the power of n ax plus b. We stretch it a little bit more this time, but essentially this expression is the same as your basic expression you encountered before. Raise it to the power of n. Just keep this in mind. Sine bracket ax plus b, the whole thing raised to the power of n. But we choose to write it this way. It's more compact. It amounts to the same thing. Now this time, I'll give you the shortcut, and then you compare it with the chain rule we are about to show you. First, you have this, which is the index. So what you do is, the index will become multiplier. So you get n. Now, when you differentiate it one time, your index is reduced by 1. So you have n minus 1. The angular expression remains the same. But you have to consider the differentiation of sign. Just the sign. You have cos. Then you would consider differentiation of the angular expression. From our previous cases, we know it's going to give us A. Summarize this by simplifying it. A times n. And this first followed by cos. So this will be the full result for differentiating something so complex. But we can understand that better with some rules in mind. But you realize that without the rules, if you just stick to the certain routine, you can do it. So I will expect you to do this in major exam. Because then you write less. If you have this clarity of thought, I think it will be very helpful. So first, the power becomes multiplier. The power reduced by 1. The expression of the angle remains the same. Differentiating sign gives you cos. Same angular expression. Lastly, the differentiation of the angular expression gives you A. Now the last step is just a rearrangement of this expression. You will see when I start showing you the chain rule in full, then it is not so compact. So what I do is to let U be sine bracket AX plus B. If that is so, Y would be U to the power of N. When I differentiate this, I have du over dx. Now, if I differentiate sine, I get cos. And I have to differentiate the angular expression. That will be A. So, the finished expression should be A cos bracket AX plus B. This, the subject is Y, so dy over the expression du. So, index here, this index will become the multiplier. And u to the power of, after each differentiation, this index is reduced by 1. N minus 1. Using the chain rule, dy over dx, dy over du times du over dx. This expression is transported here, and u to the power of n minus 1 times this expression will drop into this place, a cos bracket ax plus b. The u, remember, is actually this expression. This expression. So, a times n, go for all those constants first, place it right at the front. A is constant, n is constant, followed by u, which is this expression, raised to the power of n minus 1. So, sine n minus 1 bracket ax plus b, then cos ax plus b. This expression is actually the same as the one we had by using the shortcut approach. So you can see there is a lot more writing. Whenever we write more, the tendency is we might just make mistakes. So if you can go through the routine well in the shortcut approach, you get to the answers quicker. We'll look at this question using the shortcut approach. So this is y, so it's going to be dy over dx. dx because cos function is a function of x. Now the index here will become the multiplier, then cos, the index reduced by 1, so n minus 1. The expression of the angle remains the same. Then next will be the differentiation of cos. Cos will become negative sine bracket ax plus b. Then differentiate the angular expression, you get a. Put it all together, you have a negative sign. The two constants multiplied together, an. The trigonometrical functions with the bigger power, we write first cos to the power of n minus 1, ax plus b, the expression of the angle. Sign here with the angle. So this is the result of differentiating cos to the power n bracket ax plus b. Just as a way to revise, I think the shortcut approach we have mentioned 2 times already. We now look at the chain rule approach, just to make sure if you really have to do that, then you remember how to do it. We let u be tangent bracket ax plus b. And your expression of y would be u to the power of n. That equation up there with the subject u, so it's du over tangent is a function of x, so dx. Differentiate tangent, you get secant squared. And the angular expression remains the same. Multiplied by You differentiate the angular expression, you get an A. The full expression is A secant squared bracket AX plus B. Here, the subject is y, so it's dy. The expression of y is in terms of u, so du. So n becomes the multiplier. The power of u reduced by 1. So applying the chain rule, dy over dx equals to dy over du, du over dx. Let's look for dy over du. It's here. So you have n u to the power of n minus 1, and then your du over dx is here. A secant squared ax plus b. So the u, you recall we had tangent ax plus b. Replace it so I prefer to write it this way here for you to show you they're actually the same. The same as this tangent n minus 1 bracket ax plus b. But I take it as a raw form first. Where you have the u, I put in tangent bracket ax plus b, raise it to the power n minus 1. Then here you have a secant squared bracket ax plus b. Now the final step, I'm going to put things all in order. The constant first, a times n. This, I rewrite it into this form. Times secant squared ax plus b. So that's a lot of writing, but we got the same results. So in short, if you're going through the shortcut approach, then it's the same thing. The power here, right in front, the index becomes multiplier, followed by tangent, but the index minus 1, the expression of the angle remains the same. Then you differentiate tangent, you get secant squared. The angle expression is the same. Then differentiate the angular expression, you get A right in front. You can see why I say it's very mechanical. So if you go through the process with clarity of thought, you would not make mistake. Here are some observations. Whether it's the simplest case that we had before, like sine x, or the more complex case where you have sine to the power of n, then the angle. The sine will give you cos, cos will give you negative sine, sine will give you secant squared. The angular expression ax plus b will not change. And you can also see that when we have sine to the power n, the angular expression is the same as sine the angular expression raised to the power n. 3 parts you have to remember. The index will become multiplier. The index itself reduced by 1 in the process of differentiation. And the changes to make, sine to cos, cos to negative sine, tangent to secant squared. And then lastly, differentiate the angular expression. The summary. So this is a very raw form, so we can see how things play out. First, I'll start from the back here. The index n becomes the multiplier. The index reduced by 1. The angular expression remains the same. Followed by, now differentiating the sign, you get cos, the angular expression. Then, lastly, differentiate the angular expression here. So I put it this way so that you know the different parts you have to remember. Run through it very quickly. The index becomes the multiplier. The index reduced by 1. Remember, the angular expressions remains the same. Differentiate cos, you get negative sine with the angle here. Then differentiate the angular expression. So put it another way, deal with the index first. Then the function that is presented to you, which is tangent, so you have to differentiate that. Then the angular expression. So this summary is a good guide for you to refresh your mind on this subject matter. So that's all for today.